Hello, welcome back to this lecture series on quantum chemistry. In this lecture I am going to discuss about parity operator. Parity operator, it is denoted by the symbol pi with an hat. What the parity operator will do when we apply this operator to a function. Suppose I'll take some arbitrary function psi which depends on the variable x, y, z. Okay, if I apply parity operator on the function, what it will do, it will change the sign of the coordinates of the function. Okay, so the sign of the coordinates will change. So x become minus x, y become minus y, and z become minus z. Right, this is the role of a parity operator. It is something similar to inversion operation. So this parity operator can also be called a space inversion operator. Okay, now the function, some functions may be an eigenfunction for the parity operator. Okay, say some function, say psi of x. Okay, assume that this function is an eigenfunction. Okay, if this function is an eigenfunction of parity operator, okay, then you know very well, if I apply parity operator on this function, I will get the same function multiplied by the eigenvalue. I'll represent the eigenvalue by the symbol pi. Okay, pi with an hat indicate parity operator, and this pi represent the eigenvalue. Okay, and what are the possible eigenvalues for a parity operator? Yeah, parity operator actually take only two possible eigenvalues. One is +1, the other one is -1. Okay, only two possible eigenvalues exist for parity operator. Okay, what is the proof? The proof is this. Okay, what we have to do is you take some function, say psi of x. If I apply a parity operator on this function, I'll get same function. If it is an eigenfunction, I'll get same function multiplied by some constant, let it be alpha. So alpha is the eigenvalue. Okay, we don't know what's the eigenvalue of the function. Right now let it be alpha. Okay, now I will apply another parity operator on both sides. So if I apply parity operator on both sides, what will happen? Parity operator acting on alpha into the function psi of x. Okay, yeah, listen, when you apply parity operator to a function, you will get the what parity operator will do. Parity operator will change the sign of the coordinate. If I apply another parity operator again, okay, you will get this original function, right? So this will give you the original function. Whereas here, see, parity operator basically an Hermitian operator. Parity operator is an Hermitian operator. You know very well, all Hermitian operators are linear operators. So since the parity operator is a linear operator, okay, you can take this alpha eigenvalue out and you apply this parity operator to the function psi of x. Okay, so if I apply parity operator on the function psi of x, since psi of x is an eigenfunction, you'll get the same function multiplied by the eigenvalue alpha. So this will give me, let me write in the next page. Right, this will give psi of x equal to, I'll keep this alpha as such. If I apply this operator on the function again, I'll get an eigenvalue alpha and the same function psi of x. Okay, so psi of x equal to alpha square into psi of x. Right, since both sides we have psi of x, so alpha square value should be equal to 1. Right, if alpha square is 1, then alpha value is plus or minus 1. So eigenvalue for parity operator should be either +1 or -1. Okay, therefore eigenvalue for parity operator will represent eigenvalue by the symbol pi. So pi value should be either +1 or -1. Okay, this is the point you should keep in mind. Okay, now, and remember, parity operator is an Hermitian operator. Okay, that's another important point you should keep in mind. I'm not going to give any proof for that, but try to keep this in mind because it is a very simple one. You can easily prove it, and it is available in almost all books. Okay, now, so this is the eigenvalue. Now what I'm going to do, suppose if I apply a parity operator on an eigenfunction psi of x, if I get eigenvalue as +1, okay, suppose I have some function, if I apply parity operator on that function, if I get eigenvalue +1 and the same function psi of x, okay, so if it is +1, then we can say that the function has even parity, or you can also call this function as an even function. Even function. What is even function? If when you apply a parity operator to any function, if you get same function multiplied by +1 as an eigenvalue, then that function is called an even function. Okay, or you can also say that this psi of x is symmetric with respect to parity operator. You can also call this as this function, okay, psi of x is symmetric with respect to parity operator. That is another meaning. Okay, yeah. Now similarly, if I apply parity operator on the function psi of x, if I get -1 as an eigenvalue multiplied by the same function, listen, here also psi of x is an eigenfunction. When I apply parity operator on an eigenfunction, if I get -1 as eigenvalue, we call that function as an odd function. As an odd function, and this function can also be called as, it is anti-symmetric. It is anti-symmetric with respect to parity operator. Okay, it is an even function if eigenvalue is +1. If it is an odd function if eigenvalue is -1. Okay, keep this information in mind. Now I'll give another important information on parity operator, that suppose if potential energy is symmetric, okay, or potential energy is an even function, right? If potential energy, okay, if potential energy of a system is an even function, if an even function, that is, even function means if I change the coordinate, okay, say -x, x to -x, right? If v of -x equal to v of x, if these two are equal, we say that the function is even function, right? If potential energy is even function in a system, then the wave functions, right? The wave functions psi n of x, right, must have a definite parity. Very, very important. Whenever potential energy is an even function, then the wave function representing the states must have a definite parity, either odd parity or even parity. Okay, and usually you will get the functions, right, in this manner. That is, see, if potential energy is an even function, if potential energy v of x is an even function, then you will get the functions corresponding to ground state, first exit state, second exit state, right? It exists either odd, even, like that. Okay, suppose usually the ground state will exist as even function because ground state does not contain any node. Okay, generally for most systems, ground state does not contain any node. Okay, if suppose if it is an odd function usually contain a node, right? So since potential energy is an even function, okay, the ground state wave function should have should be an even function, right? So then odd, first exit state is odd, then next even, then odd, like this it will exist. When potential energy is an even function, then the wave functions psi, let me just put like this, psi n of x, the wave functions corresponding to that system will exist in this manner, even odd, even odd, even odd, like that. Okay, this is another information you should keep in mind, right, under parity operator. Then let me take some example and I'll show you how this is applicable in different cases. Okay, before going to that, whether a function is eigenfunction or not, okay, for a parity operator, how to check it. Okay, so let me show some example for that. Number one, say I'll take some function psi of x equal to x, whether this function is an eigenfunction for the parity operator or not. If it is eigenfunction, what will be the eigenvalue, okay, for that operator, for the parity operator. Okay, so I'll take the parity operator, I'll apply the parity operator on the function psi of x. Okay, so I'll apply the parity operator on the function. What is psi of x? Now psi of x is x. Applying parity operator means changing the sign of the coordinate. Okay, I'll put minus x, right? So this is nothing but minus 1 into x, or we can write minus 1 into, what is x? X is the given function. So I applied the parity operator on the function and I got same function multiplied by some constant. Okay, so psi of x, or x is an eigenfunction for the parity operator. Therefore x is an eigenfunction for parity operator. And what's the eigenvalue? Eigenvalue is minus 1. Eigenvalue equal to minus 1. Similarly, I'll take one more example. Actually, we can show plenty of examples. I'll take sin x. Whether sin x is an eigenfunction for parity operator or not. Okay, how to check? Very simple. Apply the parity operator to the function psi of x. Okay, so parity operator, psi of x is sin x. Applying parity operator is nothing but changing the sign of the coordinate. Okay, sign of minus x. And you know very well sin x is an odd function. Okay, cos x is an even function. So sin of minus x is nothing but minus sin x. Or I can write this as minus 1 into sin x, or minus 1 into sin x is the given function psi of x. So what does it indicate? I applied the operator to the function and I got same function multiplied by a constant. Therefore the function is an eigenfunction. So sin x is an eigenfunction. Sin x is an eigenfunction for parity operator. And what's the eigenvalue? We represent eigenvalue of the parity operator by the symbol pi. So pi equal to minus 1. Okay, eigenvalue is minus 1, right? In the same way, there are plenty of examples available. I'll take just 2 more examples so that you'll be a little comfortable with this. Okay, yeah, so I'll take another function, say f of x equal to x square plus cos x. I'll take a function like this. Whether this function is an eigenfunction or not for the parity operator. How to check? Just apply the parity operator on the function f of x. Okay, so I am going to apply parity operator on the function x square plus cos x. Applying parity operator is nothing but changing the sign of the coordinate. So let me change the sign of the coordinate. Here in the place of x I'll put minus x square, plus here in the place of x I'll put minus x, cos of minus x. And you know very well minus x square is nothing but x square. Cos is an even function, so cos of minus x is once again cos x. Okay, and you can write this as plus 1 into x square plus cos x. X square plus cos x is the given function. Therefore plus 1 into f of x. So I applied the operator on the function and I got the same function multiplied by the constant plus 1. So x square plus cos x, okay, is an even function. I'm sorry, is an eigen function for the parity operator, and the eigenvalue is plus 1. And remember, eigenvalue of parity operator is always plus 1 or minus 1. Okay, so this is very important point you should keep in mind. Similarly, you can take even hyperbolic functions. See, whether an hyperbolic function, say cos h of x, whether this function is an eigenfunction of parity operator or not. Okay, yes, you apply parity operator on the function. Okay, applying parity operator, you know, applying parity operator is nothing but changing the sign of the coordinate. Okay, and again cos is an even function, so this is nothing but plus 1 into cos h of x. Cos is an even function, right? So eigenvalue is plus 1 and the function is an eigenfunction, right? So eigenvalue is plus 1 and cos hx is an eigenfunction for parity operator. So now I think you will get some familiarity about how to identify whether a function is an eigenfunction for the parity operator or not. Okay, this is the method. Then next important point, whenever potential energy is an even function, okay, see, if potential energy, that is if V of minus x equal to V of x, so it means potential energy is an even function. Whenever potential energy is an even function, whenever potential energy is an even function, then 2 points you should keep in mind. One is the wave functions corresponding to the states must have definite parity. Okay, they may be either odd or even. Okay, so usually it will exist like this: the ground state is even function, then odd, first exit state is odd, then even, odd, like that it will go. Okay, that is one important point. And second point is that whenever potential energy is an even function, okay, Hamiltonian operator, okay, Hamiltonian operator and the parity operator, they commute with each other. That is, parity operator, commutator of parity operator and Hamiltonian operator is equal to 0. What is the meaning? The meaning is they have common set of eigenfunctions. See, Hamiltonian operator and parity operator, okay, have common set of eigenfunctions or simultaneous eigenfunctions. You can say in the other way. Okay, they have common set of eigenfunctions, right? If they commute, right? If commutator of parity operator and the Hamiltonian operator, it is equal to 0. If this is 0, then they have common set of eigenfunctions. Okay, yes, if the potential energy is an even function, then these two operators commute with each other. Okay, if they commute, they have common set of eigenfunctions. This is another important information you should keep in mind. Okay, then now I'll take some examples and I'll show you the eigen value of the parity operator for some real systems. Okay, say for example, I'll take one-dimensional simple harmonic oscillator. I'll take this case, one-dimensional simple harmonic oscillator. You know very well, in one-dimensional simple harmonic oscillator, potential energy, okay, V of x is given as k by 2 into x square. So if I change x as minus x, so in the place of x I will put minus x square. What will get? Minus x square is x square only. So again I'll get the same function. So that it means V of minus x is equal to V of x in the case of one-dimensional simple harmonic oscillator. Okay, therefore in one-dimensional simple harmonic oscillator, right, the parity operator and the Hamiltonian operator, okay, they'll commute with each other. They have common set of eigenfunctions. Okay, and another information is that the wave functions corresponding to the vibrational states, okay, psi v of x, you know very well the psi v of x formula is normalization constant into Hermite polynomial hv of root of alpha into x into the Gaussian function e power minus alpha x square by 2. Okay, see here we have x square term, so if you replace this x by minus x, this function doesn't change, the Gaussian part doesn't change, and normalization is a constant. Okay, that you need not worry about that. So the only term which keep the function whether it is odd or even, okay, it is decided by the Hermite polynomial. And you know very well the Hermite polynomial, if v is even number, Hermite polynomial will give you even function. If v is odd number, Hermite polynomial will give odd function. Okay, so we can write directly that the parity operator, when it is acting on the function psi v of x, will give you, right, an eigenvalue. Let me write eigenvalue as minus 1 power v into the same function psi v of x. Okay, so if v is even number, you know, minus 1 power even number will give you plus 1. So if v is an even number, then the functions are even functions. If v is an odd number, okay, then the functions are odd functions. So whether the function is even function or odd function, it is decided by the vibrational state. Okay, if it is a ground vibrational state, it is an even function, right? So or let me write like this: if v equal to 0, 2, 4, 6, etc., even numbers, then psi v of x must have or must be, psi v of x must be an even function. Psi v of x must be an even function. Similarly, if v equal to odd numbers, say 1, 3, 5, etc., then psi v of x must be, okay, an odd function, right? So the parity, the eigenvalue of the parity operator, eigenvalue of the parity operator, which we represent by the symbol pi, eigenvalue of the parity operator, right, is equal to minus 1 power v in the case of one-dimensional simple harmonic oscillator. Keep this in mind. Based on this, okay, you may expect questions in competitive examinations, right? Then, so this is for one-dimensional simple harmonic oscillator. In a similar manner, I'll take a three-dimensional simple harmonic oscillator. Second example, I'll take three-dimensional simple harmonic oscillator, or simply harmonic oscillator. It can be even isotropic oscillator. You know very well, in this case, potential energy is a function of x, y, and z, and it is given as kx square by 2 plus ky square by 2 plus kz square by 2. Let me put here as this is kx. I'll represent these force constants as kx, ky, and kz. Here again, if you change the coordinates, okay, plus x to minus x plus y to minus y plus z to minus z, since we have square terms here, okay, you will get the same result again. So changing the coordinates, changing the sign of the coordinates, right, doesn't change the function. So again, potential energy is an even function. Potential energy is even function, and you know very well, whenever potential energy is even function, okay, then the parity operator and the Hamiltonian operator, they commute with each other. They have common set of eigenfunctions. And here, when you apply parity operator on the vibrational state, which depends on the quantum number Vx, Vy, and Vz, okay, will give you an eigenvalue pi into the same function psi Vx, Vy, and Vz. It will give you the same function. And what is the eigenvalue? Eigenvalue in this case is minus 1 power Vx plus Vy plus Vz. So we have to add the quantum numbers, okay, that fixes the vibrational state, and put that value in the power of minus 1. That gives you the eigenvalue. Okay, suppose I'll take some state, say psi 1 0 1 state. Whether this corresponds to an odd function or even function, whether it is an odd function or even function, how to check it? Okay, just see the vibrational quantum numbers, add them. 1 plus, this is Vx and this is Vy and this is Vz, add them, you will get the number as 2. So eigenvalue equal to minus 1 power 2, minus 1 power 2 is plus 1. Okay, therefore this state psi 101 is an even function, or it has even parity. Okay, psi 101 is an even function. Okay, right, this is another important information on three-dimensional simple harmonic oscillators. Right, let me give one more point. I'll take one more example. Suppose you take an unharmonic oscillator. Right, so I'll take a one-dimensional unharmonic oscillator which obeys Morse potential. Okay, Morse potential. Right, the system, let us obey, assume that it obeys Morse potential function. What is Morse potential function? Morse potential function V of x is given as, Morse potential function V of x is given as the equilibrium dissociation energy into 1 minus e power minus some constant a into displacement x whole square. Okay, this is the formula. Here I have only x. So if I put plus x, I will get one function. If I put minus x, I will get a different function. So in this case, V of minus x and V of plus x, okay, they are not equal. They are not equal. It means the Hamiltonian operator and the parity operator, they do not commute in this case. Okay, yeah. I stop here. We can apply this. We can also check whether a function is parity, whether a function is odd function or even function, even in the case of rotational motion, or the wave functions corresponds to rotational motion. Right, we'll discuss that. Okay, when we once we discuss the wave functions and eigenvalue of energy eigenvalue for rotational motion. Okay, yeah, I stop here. We'll continue this in the next class. Thank you.